So this is section 1.5. It's our probabilities of intersections. Okay. This is actually where most of our fun happens. Okay. So we really start doing some more complicated probability problems. Everything builds up to this, basically. So we're going to start with our general multiplication rule. So if we look at our conditional probability formula, okay, and notice this tells us our conditional probability if we already know the intersection. Sometimes we want to go about it the other way. So we might know a conditional probability and we want to know the probability of the intersection. Okay, so we're just going to look at this equation and rearrange it to solve for the probability of the intersection. So basically, mathematically, what do I have to do to get the probability of the intersection by itself? Okay, so we just multiply by the probability of B, not too bad. So we get the probability of A intersect B equals, let's see, the probability of A given B times the probability of B. So notice here, of A given B, so the thing that I know, that's also the probability that I times it by. And this is called our general multiplication rule. Notice you can do, for the probability of A intersect B, you can use either conditional probability. So if we want to do B given A, then I have to times by the probability of A. If I want to do A given B, I have to multiply it by the probability of B. So we can try this. So Jim and Mary are married. The probability that Jim watches TV after work is 0.6. So this tells me just the probability of Jim watching TV is 0.6. The probability that Mary watches TV is 0.5. So that's the probability of Mary is 0.5. And then they tell us the probability that Jim watches TV, given that Mary does, is 0.8. How would I write that conditional statement? Louder. J given M. So the thing that we know is that Mary's watching TV, and that is 0.8. Okay. So we know Jim has a 60% chance he's going to watch TV. Mary is 50%. But if Mary's watching TV, then the probability that Jim watches it is 0.8. So for the first part, what is the probability that both Jim and Mary watch TV after work tonight? So now we want the probability of the intersection. Now notice in the general multiplication rule there are two different ways that I could find my intersection. The way that you choose which one is you go with the conditional probability that you actually have. So in our situation, we only have one conditional probability that was given to us. J given M, so that's the one I have to use. Okay, now which other probability do I need to multiply it by? Mary or Jim? Mary. So it's 0.8 times 0.5 should give me 0.4. So if we know that, or no, it's just the probability that both Jim and Mary watch TV is 40%. Now I might ask you, what is the probability that Mary watches TV tonight if Jim turns it on and sits down to watch? This one sounds like a conditional probability. In this situation, though, we know that Jim turned it on, so we're looking for Mary given Jim. Okay. Now, if you ever get to a conditional probability and you don't know what to do with it, I always start by writing down the formula. So probability of M and J over the probability of J. Okay. Do we know the probability of the intersection?
Yes, we just solved for it.
We just solved for it. So it's 0.4, and the probability of Jim is 0.6. So 0.6666. notice that the probability of j given m is different from the probability of m given j. And that is always true. Well, okay, I guess you could have some coincidences where they could be the same probability. But in general, these conditional probabilities are going to be different. They don't have to be the same. Okay. And notice what we just did. We originally started with the probability of j given m, and we, after a few steps, found the probability of m given j. This is actually what we call Bayes' theorem, which we'll learn about in the next section. We just did it without knowing what we were doing. And what is the probability that either Jim or Mary watch TV tonight? Okay. So what does that sound like? A union. And what is our formula for unions? Do you remember from yesterday?
Jim plus probability or whatever, minus the intersection.
Mm-hmm. And we subtract the intersection because we don't want to count it twice. So this is, let's see, what was Jim? 0.6. Mary was 0.5 minus the intersection of 0.4 gives me 0.7. So there's a 70% chance that at least one of them is going to watch TV tonight. Now notice if you'd forgotten to subtract out the intersection, what would have happened? You would have gotten a probability bigger than 1. So our next example is pretty typical. You've probably done problems like this in like junior high or high school math classes without knowing you're doing the general multiplication rule. So there are 4 blue, 5 red, 1 green, and 2 white marbles in a bag. Assume that after you draw a marble, you don't put it back before you draw the second marble. So let's find the probability of getting a blue marble and then a white marble. Okay. Now, basically, when you see the and, anytime you see an and, that is an intersection, and we know that we are going to be multiplying. But I usually just kind of think about this logically rather than trying to think about formulas. So if we want to get a blue marble first, when I first reach into the bag, what is the probability of getting a blue marble? Okay, or I guess, what is my original total? We might need to know that. 12? Okay, so the probability of getting a blue marble is originally 1/3 or 4 out of 12. Okay, and then I need to get a white marble, but I didn't put the first marble back. Okay, so what is my probability of getting a white marble? 2 out of 11, because I now have less marbles to choose from. So this will be 0.0606. Notice here I multiplied because it was an and then I just thought through what would the probabilities be for each one. As far as how you would think about this mathematically, if you wanted to use the symbols, so it would be the probability of blue and white is actually we take the probability of blue and times it by the probability of white given blue first. Okay, so that's basically what we did, is we took the probability of blue times the probability of white given blue first, and that's the correct multiplication to get back to our original blue and then white. But again, for me, it's easier to just write down the numbers and not have to try and think too much about it. Okay, so the probability of green and then red. Okay, so what is my probability of green? On the first draw, my probability of green is 1 out of 12. And then if I want a red one, the probability is 5 out of 11. and the probability of blue and then blue. So what is the probability of blue for my first marble? It would be 4 out of 12. And the probability of blue for my second marble is 3 out of 11. So 0.0909, etc. So what is the probability, so let's go to the next one, what is the probability of drawing a card from a standard 52 card deck and having it be red and a heart? Okay, so red and hearts. Okay.
Since you can be a red,
It's 1 4.
or it can be a heart if you're black.
So it's
So 13 or 52.
Okay, so it is 1/4 or 13 out of 52 because we're not doing any conditional probabilities, so we don't already know that it's red or we don't already know that it's hearts or anything like that. All we're saying is how many cards in the deck are red and hearts at the same time. All of the, sorry, no, red and hearts. There are 13 hearts, 13, I just blanked, diamonds, 13 spades, 13 clubs, right? So out of the entire deck, there are 13 cards that are red and hearts. Okay, so we know that it should be 13 out of 52 or 1/4. Let's see if we can do this mathematically. So the probability of red and hearts. Okay, well, if I was to write down my formula, okay, this would be the probability of, well, I need a conditional probability. Okay, does it matter which one? And it actually doesn't. So we're going to do this problem using both just so you can see how it could be done. So let's start with the first conditional probability. Let's just try R given H. And what probability would I need to times it by? H. So we times by the given thing. And let's see if we can figure out what both of these probabilities would be and see if we get the same answer that we get logically. So the probability that it's red if you know it's hearts. So if you know it's hearts, what's the probability that it's red? 1. And times it by the probability of hearts. How many hearts are there in the 52 card deck? 13 out of 52, so we get 1/4. And the whole reason I want to do this problem is let's try it using the other conditional probability and see if that works too. So let's try the probability of hearts given red times this time. Now I have to times it by the probability that it is red. Okay. So if you know it's a red card, what's the probability that it is a heart? So how many of the red cards are hearts? Half of them. And how many of your total cards are red? 1/2. So logically, we figured out that the intersection should be 1/4, and then we used two different formulas to find that the probability would be 1/4. So you might be noticing that there's usually a lot of different ways that I can do these problems, and you're welcome to do whatever makes sense to you to get to the final answer. So, questions on this part so far? Well, what if I want you to do this for 3 events? Okay, so instead of 2 events, what would the formula be if we had 3 events? So for this formula, what we're going to do is we're going to work through the proof ourselves, and the hint is we're going to start by looking at what the probability of C given A intersect B would be. Because there are a few times in your homework when it asks you to look at these complicated looking things, and so let's just kind of practice with working with our probability symbols. So we always start off, I said, if you don't know what to do with the conditional probability, write the formula down. So the probability of the intersection, right? So this is C intersect A intersect B. All over the probability of A intersect B. Now, looking at this, do you think it matters for C intersect A intersect B? Like, do you think those parentheses really do much there for the intersection? Okay, no. So that was one of the things we talked about yesterday, is the parentheses really don't do anything in your intersections, and also your intersections are completely commutative. You can change the order you write the letters in. So this is really the probability of A intersect B intersect C. All over the probability of A intersect B. And what are we ultimately interested in this problem? We want to know a probability or a formula for the probability of A intersect B intersect C. Okay. So can you tell me what something is that I could write down for it? Okay, if we solve for it up here, then we just have to multiply both sides by the probability of A intersect B. So if we multiply both sides by that, then we get the probability of C intersect B. Sorry, that's not. Sorry, we get the probability of C given A intersect B times the probability of A intersect B. Now, do you know anything about this? Do we know any formulas for that? We can also write that with a multiplication of conditional probabilities from up above using the general multiplication rule. So this is A intersect B intersect C is the probability of C given A intersect B times, and then the probability of A intersect B can be written as the probability of B intersect A times the probability of A. So this is what our formula is if you want to multiply or find the intersection for three events. Again, it looks complicated. We're never going to memorize the formula and try and find things by plugging into the formula. We'll just kind of do our questions logically. But that's what it would be if you were ever curious. And then if you want to have multiple events, here's your general formula. So A1 intersect A2 up to AN. So a multiple intersection. We start with the probability of A1 times by the probability of A2 given A1 times the probability of A3 given A2 and A1, okay, times the probability of A4 given A1, A2, and A3, etc. Okay, so you can kind of see the pattern that's happening here. But here's what I'm actually going to ask you to do, the types of questions. So a license plate has 6 symbols. The first 3 symbols are letters from the English alphabet, and the second 3 symbols are numbers 0 through 9. A symbol cannot be repeated. What is the probability of having a license plate that says Gen 1, 2, 3? Okay. So I want a J, then an E, then an N, then 1, 2, 3. Okay. Symbols can't be repeated. Okay. We know that the first 3 symbols have to be from the alphabet, so if it has to be from the alphabet, what's the probability of getting a J? 1 out of 26. Okay. Now, I've already drawn out the J. What's the probability of getting an E? 1 out of 25. Because it says the symbol can't be repeated, so J's aren't in there anymore for consideration, so we only have 25 letters to choose from. Probability of an N would be 1 out of 24. Okay. Now it tells us that the next 3 have to be numbers, so the probability of a 1 is 1/10. 2 is going to be 1/9, and 3 is 1/8. And what do you think I need to do with all of these probabilities? Okay, we multiply them together. So anytime you need N, so you need them to all happen together, we multiply the probabilities. So this is 1 out of, if I typed it correctly, 11232,000. So let's see, this is 8.9 times 10 to the negative 8. Now, who remembers doing problems like this in any previous math classes? Okay, so remember doing this. Did they tell you that you were doing the multiplication rule that looked like this? No. Okay, again, this is what I'll give you on the test. It shouldn't be that difficult. It's not like we're trying to use a complicated formula. Just know that that is the formula that you're using without realizing it. So, questions? So this next part deals with independent events. Okay. So two events are independent if they don't affect each other. Okay. So independent, they don't affect each other. Okay. So that means that if A and B are independent events, then the fact that B has occurred does not affect the probability of A occurring. That makes sense, right? If they don't affect each other, then if you know B happened, that shouldn't change the probability of A happening. Okay. And how do we write that in symbols? That means that if they're independent, then the probability of A given B is just equal to the probability of A. So basically they're saying the probability of A doesn't change whether or not B happens. So it doesn't matter if you know that B happened, the probability of A doesn't change if they are independent. So this next thing is a pretty classic problem. So in a soft drink taste test, each of 1,000 customers chose between two colas, cola 1 or cola 2, and stated whether they preferred their cola drink sweet or very sweet. Unfortunately, some of the survey data was lost, and the following information remains. Okay. And we need to fill in our contingency table for the next meeting. So we know first that 683 consumers preferred cola 1 to cola 2. So, where do you think that might go in this table? Okay, a total, and for what thing? Okay, so the first row for cola 1, the total number of people that liked cola 1 was 683. And our grand total was 1,000. So if you know that 683 people liked cola 1, how many people liked cola 2? Okay. 317. Because they have to add up to 1,000. Okay, the next thing is 620 consumers preferred their cola sweet. Okay. So that means that the total for sweet is 620. Which means that my total for very sweet is 380. Let's see, and then 85% of the people who liked their cola sweet preferred cola 1 to cola 2. What should we do with that?
Find 85% of 620.
Okay. So 85% of 620, because there are 620 people that liked their cola sweet, so 0.85 times 620. Anyone already do that? 527. So that means of the people that liked it sweet, 527 liked cola 1. Okay. Once you know that much, can you find everything else on the table? Okay. We're just adding, subtracting, or just subtracting. So, for instance, I could do 683 minus 527. And that tells me that the number of people that like it very sweet and cola 1 are 156. Let's see, and then 620 minus 527, 93. So, and 224. So we filled everything in the table. And I want you to find the following probabilities. So the first one is the probability of C1. So the probability that they like cola 1. Okay. So what would you do for this? Okay. So the total number of people that like cola 1 are 683, and the total number of people are 1,000. So we're at 0.683. For the next piece, let's find the probability that they like cola 1 if we already know they like it sweet. So what would you do for this? Okay, so we could start by writing out the formula. So we want the probability of C1 intersect S over the probability of S. Okay. So how many people in the table like C1 and S? Total number of people who like C1 and S on the table are 527. And the total number of people, sorry, I'm skipping things. It says probability. 527 is not a probability, is it? The probability is 527 out of 1,000 because there are 1,000 people. And then how many people like it sweet? There are 620 people that like it sweet out of a total of 1,000. Now what happens to those 1,000s? They are going to cancel and we get 527 out of 620. Now how many people wanted to find it this way just by writing down the 527 out of 620? Okay, that was probably natural to about half of you. Okay, so this is just doing it with a reduced sample space. Notice you are going to get the same answer as if you do it the long way. Okay? You can do it whichever way makes more sense to you. Okay, some students love to do it this way. Some students get really confused when I start doing it that way. So either way. What decimal does that give me? 0.85? Oh, we already knew that, didn't we? Okay. So the probability, I should change that for next time, I guess. So the probability that they like cola 2, if we already know they like sweet stuff. Okay. So let's actually write it out just for practice. So cola 2, if we know they like sweet stuff, so this is and sweet over the probability of sweet. So the probability of the intersection, the people up there that like cola 2 and sweet stuff, is 93 out of 1,000. And the probability of sweet stuff, the total sweet stuff, is 620 out of 1,000. So we're at 93 over 620. So 0.15. Okay. What do you notice here about 0.85 plus 0.15? They add up to 1. Let's see, the probability of S given C1. So let's just do it the shortcut way. So how many people like the sweet stuff if you already know that they're in cola 1? 527, and total number of people that like the cola 1? 683. So 0.7715. Now just to give you more practice interpreting things, so like what would comparing the probability of C1 given S and probability of C2 given S tell us in words? Okay, so if you're just talking to your friend, what would you tell them? Your friend that has not taken statistics.
C1 is sweet.
C1 is great. If what? Okay, so you said C1 is great. Okay. If we already know that they like C1. Okay, so, or not C1, sweet. Okay, so they're both conditional on sweet. So if we look at these two things, so if we already know that they like sweet, then it's 85% chance that they will like C1 and only 15% chance that they will like C2. So if we know they like sweet cola, they are more likely to like or more likely to prefer colon 1. Now, mathematically, what we're interested in here is if you come back up and look at the probabilities, notice that the probability for C1 given S and the probability for C1 were different. So because we know that they're different, we know that the probability of event C1 is influenced by whether or not you have the event S. So the probability of whether or not they like cola 1 is influenced by whether or not you know they like sweet colas. And this means mathematically that our two events are dependent. The opposite of independent is dependent. So in the future, if I ever ask you to prove that something is independent or dependent, this is what you have to check mathematically. You should check the conditional probabilities. So for another example, so we had a summary of gender and types of job at a university. And I'm going to ask you, does your gender affect which type of job you get? Okay. So this is something that I can see you actually need to do. Okay, in the future, if you ever worked in anything with statistics, is they might ask you, does something affect something else? Okay. So what kind of conditional probabilities do you think you might want to look at here? Now notice there would be a lot of possible choices, but what are two probabilities that we could look at that would answer this question? Which two probabilities would you compare?
The probability of a male being in a job and the probability of a female being in a job.
Okay, so we could compare it that way. Let's pick one specifically to focus on. Okay. So we could compare them. Let's go with the mathematically if we need to compare one conditional probability to a regular probability. So do you want to look at males or females? Doesn't matter, just pick one.
Males.
Okay, we're going to look at males. Okay, and pick a job that you want to focus on.
Faculty.
Okay, males and faculty. So which conditional probability do you think is going to be of more interest to me here? Do I want to look at the probability of faculty given male or the probability of male given faculty? Which one is going to tell us more about whether your gender affects which job you get? Okay. It's actually going to be this one. Okay. Now, mathematically, it doesn't really matter because if gender is independent of job, then job is also independent of gender and vice versa. Okay. But as far as like logically what it makes more sense to tell your boss, you're going to want to concentrate on, does your gender affect your job? That's what he asked, so that's the conditional probability that makes more sense to me to look at. So let's find the probability of being faculty if you already know that you are male. Okay. So how many people on the table are males and faculty? 110. And how many total males are there? Since we know that they're males, so we're focusing on the male category, so there are 200 males. So 0.55. Now mathematically we defined it as we need to compare this to which probability? The probability of being faculty. Okay. So you compare the probability of faculty and the probability of faculty given male to see if whether or not you know they're male changes the probability of being faculty. Okay, so what's the total number of faculty at this university? 120 out of my total people at the university is 300. So 0.4. Okay. So the overall probability of being faculty is 40%. But if you know that you're male, the probability of being faculty suddenly jumps to 55%. Okay? So do you think that your gender affects which type of job you get at this university? Okay? Yes. So gender affects job type. So they are dependent.
So when you first did the probability of faculty given male, how did it write out the formula? Conditional.
Because I'm one of the people that it's natural for me to just look at it on the cross contingency tables, but I'll write it out. So faculty given male, the formula is the probability of faculty intersect male divided by the probability of male. So what was the probability of faculty and male? So there were 110 people that are both out of my total 300 people at the university. And total males at the university are 200 out of my 300. My 300s cancel and I get 110 out of 200. Yep. So at some point, I'm probably going to ask you, will you check and see if these events are dependent or independent? And the way that you need to check is by comparing your conditional probabilities. Questions on it?
So you're saying that if those two probabilities would have been the same, then we'd know they were independent?
Yes. Yep. Then we have our multiplication rule for independent events. Okay. So if A and B are independent events, then what happens to this formula? Okay, so we have the probability of A given B equals the probability of the probability of A and B equals the probability of A given B times the probability of B. Well, if they're independent, what happens to this conditional probability? Okay. So look up further on the page. If they're independent, what is the probability of A given B equal to? Probability of A. So we know that the probability of A given B equals the probability of A if they are independent. So this really just becomes the probability of A given B, of A and B, I'm having a hard time today, is the probability of A times the probability of B. Okay. Notice that's a much nicer formula, and that simplifies our life a lot. Okay? But this only works if your two events are independent. And so it actually turns out that, so remember up above I told you there were two conditions to check independence. These were my two conditions to check independence. And it turns out that you can prove that if one of them holds, then the other one holds. And you can prove that if any of these hold, then the third condition also holds. And so when it comes to checking independence, you can actually check any one of these three conditions. Okay? So on the test, when I say, are these two events independent, show me mathematically, you need to show me that one of those three things happens. You don't have to show me all of them, just one of them, whichever one seems most convenient. This next example should look fairly familiar. So there are 4 blue, 5 red, 1 green, and 2 white marbles in a bag. So this is a total of 12. Assume that after you draw a marble, you put it back, and then you draw a second marble. Okay. How is this different from the last problem? Okay, the total stays the same. The fact that we put it back means that these are actually going to be independent events. They're going to be independent events because what you get on your first draw will not affect what you get on your second draw. So if I want the probability of blue and then white, well, what is the probability of getting a blue one? 12ths or 1/3 times, because it's an and then I want a white one. So a white one is 2 out of 12. So 0.0555. And if I want a probability of a green and then a red, let's see, so green would be 1 out of 12, and the probability of red is 5 out of 12. Notice my denominator stays the same because I put the marble back. And then, of course, our textbook likes to give us as many fancy-looking formulas as they can, make you feel like you're getting your money's worth. And so we have a formula for the multiplication rule for independent events, multiple independent events. And so basically for this one is you can have the intersection for as many events as you want, and all you have to do is multiply up all the individual probabilities. Not too bad. Okay, because they're independent, you don't have to worry about conditional probabilities or anything. You just multiply up all the probabilities of each event. So for example, we have our license plate again with 6 symbols. Okay, same setup as before, but a symbol can now be repeated. Okay, and because it's repeated, that means that these are all going to be independent events. They don't affect each other. So now when I want my gen 1, 2, 3, what is the probability of the J? It'd be 1 out of 26, and the probability of the E is still going to be 1 out of 26. The probability of the E is 1 out of 26, sorry, the N, and the numbers are 1/10 for each of them. So we get 1 out of 17576,000. It's 5.68 times 10 to the negative 8. Okay. Did my answer change quite a bit from the last one? Remember what the last one was? I think it was 8 point something times 10 to the negative 8. So which, between this example and the example where we couldn't repeat a symbol, which situation gave me a higher probability to get gen 1, 2, 3? Okay. The first one that we did, where they can't be repeated, why? Why is that a higher probability? Because we reduce the sample we were pulling from. There's not as many license plates to choose from if you don't repeat it, and so we have a higher likelihood of getting a gen 1, 2, 3. This next example, we're going to do problems like this quite a few times. So let's say that I have a 0.8% probability of correctly answering any multiple choice question on a quiz, because I've studied enough now, and there are 3 questions. So what would be the probability that I get all the questions correct? So I want to get a correct, correct, correct. Okay. How would you find that probability? These are independent events, so I can just do the probability of getting the first one correct times the probability of getting the second one correct times the probability of getting the third one correct. So this would be 0.8 times 0.8 times 0.8. So 0.512. Now, do you remember we've actually done a problem with quiz questions where we had the 3 questions and we looked at the probabilities, but how did we have to find the probabilities at that time? Before. It was when it was true, false, so all of my possibilities were equally likely, so all the probabilities were 1/8. Do you remember that problem from yesterday? But once we got to something more complicated, they weren't all equally likely, we didn't know how to find the probabilities until now. But this is what you want to do. So if you want the first one correct and the second one correct and the third one correct, you're doing an intersection, and so we just multiply the probabilities. So the probability, if I want to get them all wrong, so wrong, 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 so I need the first one wrong, and then the second one wrong, and then the third one wrong, what would that be? 0.2 times 0.2 times 0.2. So 0.008. What is the probability of my answers being correct, wrong, and correct in that specific order? So, correct, wrong, correct. What do I need to multiply for that? So the probability of correct is 0.8, the probability of wrong is 0.2, and the probability of correct is 0.8. So 0.128. And then this next one is usually what trips people up. So what is the probability that I answer at least one question correctly? What? Okay. It will not be 0.8.
0.8 divided by 3.
And it won't be that either.
0.992.
Okay, why?
Because, well, if we take the opposite and say we get all questions wrong, we've already calculated that, and so then it's just 1 minus that.
Okay, so the complement is all wrong. So the probability of at least one right is 1 minus the probability of none right, which you said we've already calculated to be 0.008. So the probability that I get at least one right is 0.992. And as I said, this is a problem that trips everyone up. They try and either do things that seem more simple, but it really doesn't work. Okay? So what's really happening in this problem is you would actually have to consider, this is what I kept focusing on yesterday, what are all the possible ways that I can get at least one right? So at least one right is I could get a correct, wrong, wrong, or a correct, wrong, correct, or wrong, correct, wrong, etc. And there are 7 of these possibilities, and I would have to find the probability for each one of these possible outcomes and add up all those possibilities, all those probabilities. Or we use the complement rule to figure out that it is 0.992. Okay. In fact, I can almost guarantee that we will have a question like this on the test just because it is a fairly commonly missed question. I actually have another handout for this that will kind of walk you through all the steps to help you realize why you need to do this, I think. I'll post it on Canvas today, and if you guys felt confused while we're going over this, you can work through that, and it should help you feel better about this concept. Our next example is pretty similar. So let's say that the probability that a person has a positive test result, so I think we're doing like a medical test for something, is 0.02. Assume that the results for different people are independent. So hopefully whether or not I get a positive doesn't affect whether or not you get a positive. If one person takes the test, what is the probability of a negative result? So 1 minus 0.02 gives me 0.98. That's pretty simple. So just one person took the test. That's all it is. We have a 0.98% chance of getting a negative. Okay, now let's say if 5 people take the test, what is the probability that they all have positive test results? What would you need to do for that? So I need the first person to be positive, and the next person to be positive, and the next person to be positive, and the 4th person to be positive, and the 5th person to be positive. So what do you think I need to do? Okay, just times them all together. So one person being positive is 0.02, so we're going to do 0.02 times 0.02, 0.02, 0.02, 0.02. Notice this is 0.02 to the power of 5. So 3.2 times 10 to the negative 9th. So even though the probability of one person getting this positive test result is only 0.02, by the time if you want all 5 people in a row to have a positive test result, you're at 3.2 times 10 to the negative 9th. Let's say you want the probability, so 5 people take the test. We want the probability that the results in order are positive, positive, negative, negative, and negative. So we want positive, positive, negative, 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 negative. Okay, so what probabilities I need to multiply together for this? So probability of positive is 0.02. 0.02. Probability of a negative for one person is 0.98. We need the fourth person to be 0.98 and the fifth person as well. So we're at 3.76 times 10 to the negative 4th. Now those are all simple enough to do by hand. Okay. But what if I want 50 people to take the test? What is the probability that they are all negative? So the probability of 50 negatives. Okay, how would you do this? Okay, 0.98 to the 50th power, because I need 0.98 times 0.98 times 0.98. So 0.364. But now if I say, if 50 people take the test, what is the probability of at least one positive? Okay, 1 minus 0.364. So we need to use the complement rule here. So the probability of at least one positive is equal to 1 minus the probability of no positives. And how do you get no positives? If you have no positives, that means that you had 50 negatives. So 1 minus 0.364 is 0.636. Questions? So at this point, you would technically be able to finish everything in the section, but we have a technique that makes things easier for us. Okay? So we like to do probability trees. These are useful for independent or dependent events. Okay? Either way. So, for example, we have the personnel manager gives an aptitude test to all their newly hired employees in an attempt to determine the potential. Based on the past results, the personnel manager knows that 70% of the new employees pass the test and the remainder of the new employees fail. Okay. Among the new employees who pass the test, 60% will end up in a management position. So to me, that sounds like we are talking about some conditional probabilities here. So of the people that pass, these are people that end up in management. So that's a conditional probability there. Among the new employees who fail the test, 20% will end up in a management. And the question that I want us to tell them is, of all the employees that are hired and take the aptitude test, what percentage will end up in a management position? Okay. And the easiest way to do this is we're going to make a tree diagram. So what comes first in this situation? What's the first step? Pass or fail. Okay. What is the probability of passing? 0.7. The probability of failing is, well, if the probability of passing is 0.7, the probability of failing would have to be 0.3. So really, we just found this is the probability of passing is 0.7. Okay, and this is the probability of failing. I don't usually write the probability notations out when I do this. I just draw the tree, but I'll do it this first time. Okay, after you either pass or fail the aptitude test, apparently this does not affect whether or not you are hired. Okay, you can go on to either end up in management or not end up in management. And they didn't tell us a symbol for not management, so I'm just going to do not management. Okay. So if you pass the aptitude test, because that's the branch I'm on, so if you pass the test already, then what's the probability that you become a manager? 60%. Okay. What do you think this branch should be? 0.4. Okay. So it does end up that every set of branches should always add up to 1. Okay. So of those that pass, 0.6 will become managers and 0.4 will not become managers. And even if you fail the test, you can still go on to become a manager or a not manager. If you failed, what was the probability of becoming management? 0.2, which means the other branch must be 0.8. Now, when I did this branch, okay, was this branch the probability of management overall? Okay. No, that branch was not the overall probability of management. This branch was the probability of management if we already know you passed. Okay. So really these were all conditional probabilities. So as you go on and you draw your tree, each branch is one further conditional probability. So you're saying, okay, I already know you passed. Now what's the probability of being in management? So these are all conditional probabilities. Okay. Now thinking back, if I had these two probabilities, so this is the probability of P, this is the probability of M given P, what would happen if I times these two numbers? What would you end up with? So if I multiply them, so P, probability P times probability of M given P, that gives me, if you remember, M and P. Okay. So if you multiply along the branches, you always get the probability of the intersections. So 0.7 times 0.6 gives me 0.42. Is that right? Okay. So if you multiply along branches, you get the probability of the intersections. So if I multiply along the next set of branches, so 0.7 times 0.4, well, this would be the probability of M and not M. Wait, doesn't make sense. Pass and not M. So 0.7 times 0.4 should give me 0.28. If I multiply along the next branch, so 0.3 times 0.2, this is the probability that they failed and they became management. So 0.3 times 0.2 gives me 0.06. And the last set of branches would be the probability that they fail and they are not management. Of 0.3 times 0.8 gives me 0.24. What is the total if I add all of these up? Anyone checking on their calculator? It is going to be 1, okay? And if you draw your tree correctly, then when you find the probability of all the intersections and add them up, you should get 1. But we still haven't actually addressed the problem. So the problem was, what percentage end up in management? Okay. This is why we draw a tree diagram, because it makes it really easy. So we want the probability of management. Okay. What we're going to do is we're just going to go through and we look at these intersections, and if you find each intersection that includes a management, so this one includes a management, and this one includes a management, you can add those together. So this equals the probability of management and pass plus the probability of management and fail. So 0.42 plus 0.06 gives me 0.48. Now I told you that you probably wouldn't end up memorizing that formula, but we would use it. Okay, this was a formula that we found before, and we figured out that probability of M and P plus the probability of M and F will give me the probability of M. Okay, but I just remember, okay, if I draw my tree and then I circle everything that has an M in it and add them together, that will give me my total probability of being in management. Okay. Otherwise, I think it'd be very complicated to try and memorize all the formulas. So for the next part, let's say we have a randomly selected employer is not in a management position. What is the probability that he passed the aptitude test? Okay. This sounds to me like what? A conditional probability. Okay. What's the part that we want to know? So we want to know if they pass. And the part that we know is that they are not management. Okay. Well, remember I've told you, if you don't know, let's just start by writing out the formula. So we need to know the formula that they pass, the intersection that they pass and they are not management, over the total probability that they are not management. The reason we want the tree is our original problem did not give us any one of those probabilities. Okay? But I think with our tree diagram, we now know enough that we can find each of these. Okay? So look back up at your tree. Did you anywhere see a probability of pass and not management? Wait, is that right? Pass and not management? Okay. So pass and not management. Do you see that anywhere? Let's see. So pass and not management is my 0.28. So I found that probability. And then I need the probability of not management. Okay, did we find that anywhere? Okay, no, but if I know the probability of management is 0.48, then what is the probability of not management? So 1 minus 0.48 gives me 0.52. Okay, so I could do it that way. What other way could I do it?
Add it up.
Okay, find every probability up here that has not management. So 0.28 and 0.24 and add those together. So we could do 0.28 plus 0.24 gives me 0.28 over 0.52. So 0.538. Okay, so the probability that they passed, if you know that they're not in management, is still 53%. Okay. So questions on this tree diagram. Okay. It'll probably take a few more trees before you feel really comfortable with this. Okay, so we'll finish it tomorrow, but you do know enough that you can do everything, or at least try and start on section 1.5 tonight.